Hello and welcome to Microsoft Hates Greg. My name is Greg Deckler, and today we're going to be taking a little bit deeper look at this flat versus star schema. So these are the results from the 100 million fact table flat table, as well as the 100 million fact table star schema, right? That I just a couple videos ago basically posted out there. And the results to a lot of people may be surprising, probably mostly because you've been fed a decade's worth of half truths and lies around how Power BI actually works. But anyway, I'm going to explain why the fact that the flat table is just as performant as the star schema. If not, you could look at it that the DAX actually performs about 10% faster, right? Why this makes absolute sense, and is not surprising at all if you actually know just the basics of how the Vertipaq engine works under the hood. Now, again, none of this was surprising to me because I've been down this route before with the no calculate approach, where everybody was like, "Greg, that's terrible. No calculate will never be as performant as using calculate." Blah 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 blah, and they turned out to be wrong, and we proved them wrong over and over and over again. Even though some idiots still spout that nonsense, it's not true. And actually, the reason it's not true shares a similar reason with why the flat table is kind of OP in terms of raw performance versus the star schema, right? So they actually have there's a common thread as to why both of these approaches work really well. And it's because of how the Vertipaq engine is structured and how it kind of works under the hood. So we're going to explain all of that, hopefully without as little technical jargon in that as possible, right? I'm not going to call this a deep dive on the Vertipaq engine because I don't want to get into a bunch of stupid technical stuff that you don't care about. So we're just going to hit the basics, right? Now, I do have a poll out there, which is how many rows in your largest fact table, less than 100 million, 100 million to a billion, 1 billion to 10 billion, or 10 plus billion. So I'll link this poll, so go out there and vote. Well, no, that's not going to work. What I'm going to do is I just posted this, but by the time this video comes out, the results should be in because I set it for like 3 days. So at the end of this video, I'll also tack on an additional piece where I talk about the results of this poll, right? All right. But if you're a member of my channel and you have early access to the video, go out and vote, right? And let me know how large your largest fact table is. Okay, so let's get into the meat of this presentation. Vertipaq under the hood. Now, the way Vertipaq engine works is, again, a table, right? This is how tables are stored. A table usually has one partition, right? Sometimes there's more than one partition, right? That's how incremental refresh works, but usually a table has one partition, and then within that partition, it's basically some segments that have about 1 million rows in each segment, okay? And then they have segment stats, min max, desync count, like let Vertipaq skip whole chunks, right? Segment elimination during queries, right? If it knows that the information it's trying to find isn't in that segment, right? There's metadata that's stored about each of these segments. Okay, enough about that. Columns are stored separately, right? Columns are stored separately. A scan of a few columns never touches the others. So the best thing that I found to explain this is going back to here. This is a good thing. This comes from House of Concepts on YouTube. And it goes through. And so if you have a table like this with 3 columns, the columnar engine, the Vertipaq engine, actually splits that into 3 independent columns, basically. There's metadata that ties them all together that's at the table, but the way they're stored, it actually stores these as separate. So if I'm scanning product name, it's never going to touch sales, right? That kind of stuff. If I'm looking for a distinct count of product name, it's going to scan this. It's never going to touch this or this, right? This is just how it works, all right? All right, so back to our presentation here. So now you have encodings and compressions, right? There's these things called dictionary encoding, value encoding, additional tricks like RLE, row level encoding, or run level encoding, run length encoded, right? So essentially, and probably the easiest way to explain this is going back to this guy right here. So this is a good Monahel Ahmad. I probably just butchered that. But wrote this blog article back in 2021 where they do a really good job of breaking this down simply without a lot of technical garbage and jargon and stuff being thrown around. So essentially, you have a column, right? We know this, each column is stored separately. Basically, it gets each one gets an index. So New York is maps to 0, Tokyo maps to 1, London maps to 2, and it creates a dictionary basically of these. So it basically kind of like a lookup table, right? So it kind of replaces New York with 0, Tokyo with 1, 2. So that's how it's stored. And then it uses this dictionary to basically, you know, I guess reconstitute the actual values themselves, right? So this is how the whole compression works a lot in this. Dictionary coding is by far the most common, right? This is how the columnar compression works. Now you also have value encoding. So the way value encoding works, it works for numeric things. So let's say, for example, the minimum in this is 124. So it takes that minimum and subtracts it from every one of these values. So now instead of having 204 as your largest value, now your largest value is 80. So there's fewer bits required to represent 80 than there is to represent 204. So therefore it compresses, right? Now the other one is run length encoding. Run length encoding says, oh, I have this, and this is where sorting is so important, like within the Vertipaq engine. When if you notice when it imports your data, there it's always got kind of sorted in a certain manner. Well, that's to optimize in a lot of cases run length encoding. So run length encoding says, oh, I have 200 is here 3 times, and then 50 is here twice, and then 90 is here 5 times or 6 times, and then 160 is here twice. So the way it'll encode that is it'll say, okay, 200, it starts at 1, it counts 3, right? 50, right? Starts at 4 and counts 2. Now it actually doesn't store the start column because that's easy enough to re-engineer from the counts. But anyway, so that's another trick that it does in order to store this information. All right. So that's just the basics of how the Vertipaq engine, works and encodes things. And again, each column has its own dictionary, right? The ID for USA in table A's country column, nothing to do with, the ID for, USA in table B's country column, right? So they're all independent of one another. Now, the more important thing to this whole discussion is how relationships are stored. Okay. So, you're thinking that, oh, I'm building these relationships and this and that. Well, it doesn't store it that way. In fact, it's just metadata in indexes, right? It's not pre-joined data or anything else like that. So essentially, it creates internal indexes on the columns that participate, right? There's a relationship record is stored as model metadata. And again, there's this hidden blank row. This is where you get values versus distinct, right? Where there's this hidden blank row that is for unmatched values, right? Where referential integrity is not perfect, if you will. So now, you have to understand you have tables which are stored as independent columns, right, and compressed that way. And then these relationships are stored as basically metadata within the Vertipaq engine. So what happens when you actually do a filter from this dimension column over here, this dimension table over here, to the fact table, right? What happens? Well, what happens is that basically you filter on the lookup. So Vertipaq would resolve USA via customer's country dictionary and applies a bitmap over the customer rows. Okay. It can then use that bitmap, right, to translate that to keys, right? Because now it has to figure out this is the dimension USA. It maps to this key, which then maps to the fact, and they can use those keys then or keys to map the fact row tables, right? So it maps those key values to the exact row IDs in the sales, like the fact table, right? And then it applies the bitmap to the fact table, right? So here's the important part. Because each column has its own dictionary, the engine does not reuse IDs across table. Instead, it turns filtered values on the lookup side into the actual values, then finds the corresponding value IDs within the fact column's own dictionary and applies those via its column index, right? It's the essence of relationship transversal in Vertipaq, okay? So if you think about it, you can already start to understand why flat tables and even the no calculate approach, which kind of treats a lot of things as if it's flat tables, why it works so well and is so fast. Because instead of going through 4 different things that it has to do when it's using a star schema or using calculate, right? It does one, right? It only needs to do one step. So if I do a filter against a fact table, it has to do one step, right? It applies the bitmap over the matching rows and it's done, right? Versus all this other nonsense that it has to do, right? So you're adding, so by adding these star schemas and this relationships and that, you're actually adding 3 additional steps. You're adding real work with every relationship that you define within your model in terms of trying to traverse from that dimension table to the fact table. Okay, that's in the essence. If you don't understand anything else, understand this slide, right? This is why flat tables like kick ass as far as speed and that, because they don't have to do all this other nonsense, right? Okay. So again, relationships cost something, even though the Vertipaq's in memory, right? You still have to go through all those extra steps, right? So now this probably isn't slow on 100 million rows, right? But it's still work, and a flat table skips all of that. So your filters and aggregations hit one dictionary space directly, and you're done. You don't have to do all this relationship traversal and anything else. Okay? So flattening your data model, right, your semantic model, can actually improve like column locality and segment pruning, right? So it's, again, it stores columns and segments of 1 million rows. When you flatten out a model, attributes like customer region, product category become additional columns on the same table, right? If you filter region equals Europe, Vertipaq can like skip entire segments immediately because the segment stats are now in the same table. It knows which segments it cares about and which ones it doesn't, right? In the star schema, the same filters exist on separate lookup tables. So the engine has to go and traverse those relationships because before it knows which fact rows to touch. All right. All right, so dictionary density and compression may improve. Like, so a flat table actually often compresses a lot better than what you might expect because of all the repeated dimension values, right? And because they're just, correlated patterns that the Vertipaq can exploit, right? Sorting, you can do a lot of, fancy stuff with the sorting with, again, the run length encoding, right? Star schemas on there, they have separate dictionaries for every dimension. So fact columns with surrogate keys are often high cardinality integers that compress worse than repeated low cardinality categorical values in a flattened structure. All right. So I know this is a bunch of word vomit coming out, but we'll wrap this up with a summary here in a second. So less context tradition and fewer filter propagations, right? So DAX measures implicitly trigger context transitions or calculate operations that must propagate filters through relationships. When everything lives in a single table, there's no propagation, just direct column filters, which can drastically simplify the internal query plan, right? Again, remember, the DAX you write and all of that sort of stuff that you write is just suggestions to the DAX query engine on how to go and pull that information efficiently, right? And perform the calculation, right? So again, it goes back to the query, the storage engine, the query engine, all of that sort of thing, which this is why, again, no calculate and kind of because no calculate kind of treats in a lot of cases treats things as if it's a flat table, right? It filters on the fact table, right? Which everybody's like, oh, that's terrible, Greg. It does that. Well, it actually turns out to be quite fast when you do it that way because you skip a bunch of steps, right? So anyway, so the whole concept of flat versus star schema, yes, perhaps at scale, at some point the star schema becomes faster than the flat table, right? Maybe at 1 billion rows or 10 billion rows. We don't, maybe there becomes an advantage of star versus a flat schema. But the vast majority, I'm going to guess like the poll isn't closed yet, but I'm gonna guess that it's gonna be that 1 billion rows or more is gonna be probably like 5 to 10% of like all semantic models that are out there and stuff like that. And that's just the people. That's the largest fact table that they have to deal with, right? But that's just okay. That's one among many. So the actual number of probably 1 billion or 10 billion row fact tables that are out there in the wild in industry is probably incredibly low. It's very, very tiny percentage, right? So it's not correct to talk about, I don't think, flat table versus star schema in terms of speed and which one's better, because the flat table, sorry to say, is going to win most of the time. Okay, it's going to be faster, right? Just because of the number of steps and the cutting out the relationship transversal and all that sort of stuff. You don't have to do any of it, right? So now, some of the things you can say is the compression ratio. Flat tables is going to be sometimes going to be higher in terms of the actual ratio of compression, but it's going to be rather limited, right? And we saw this, right? Versus star schema is going to be usually better overall because small lookup tables compress independently and they compress really well. And we saw this within our versus star schema, right? The actual memory consumed by the semantic model was higher in the flat table versus the star schema, but again, do you really care about that? And that's all the time. The model size, right? The model size is going to grow with every new attribute versus star schema, it's not, right? And then scalability, you're going to have slower refreshes and larger memory footprint, right? When the data grows beyond the cache, right? Versus the star schema scales linearly, dimension reuse, blah, blah, blah. But again, for like 80 to 90% or even 95% of data models, do you care about any of that? Is the question. And I would say for 90%, probably it doesn't matter, right? Uh, so why flat tables can be faster? Again, avoids relationship transversal. Segment pruning can be more efficient. Compression can overperform if the data is sorted or highly repetitive. Dictionary lookups are simpler, right? One single dictionary space. And DAX formulas avoid additional context propagation overhead. So in short, right, Vertipaq's query pipeline is incredibly fast at scanning compressed columns, but filter propagation across relationships introduces real work, right? This is why a fully flattened pre-join table can outpace and outperform a perfectly modeled star schema. So what I want you to think about with this um, is all of the lies and half truths that you've been told in terms of how this works, in terms of star schemas being better than flat tables and all this other stuff, right? It's all mostly lies and half truths, right? And it's all, a lot of it's built upon benchmarks that are not repeatable, not independently verifiable, right? Versus what I'm presenting to you is all repeatable and independently verifiable, right? I've linked out all of the materials that I've used in, they'll be in this video. They're in my previous videos as well. There's folders, contains all the stuff. Go do it yourself, right? Don't trust what I have to say. But the unfortunate aspect of all of this is that most people that are out there are going to aren't very good at independent thinking, right? They're just going to be like, oh, this authority figure said this, even though they didn't, you know, didn't allow their benchmarks to be independently verified or or anything like that. They said this, so it must be true, and so da da da. Star schema is forever, right? It the actual the reality is it's a lot more nuanced than that. It's not that, oh, star schemas are always better, than flat tables, right? Because they're not, especially in terms of speed. Now there's other reasons why you might want to use star schemas, right? I mean, especially for like multi-fact semantic model, semantic models, right? Multi-fact table semantic models, that sort of thing, right? Absolutely. I mean, there's other reasons to use star schemas other than flat tables, right? There's other reasons to use them other than speed. In fact, most of the time, I'd say the vast majority of the time, speed is not an advantage of star schemas. It's just not. Okay. And as I just as I showed, like if you asked anybody, like, well, what if you wanted your DAX to run 10% faster? Most people are like, hell yeah, I want my DAX to run 10% faster. Well, we just saw that with the flat versus star schema, that the flat table ran about 10% faster in terms of the DAX and that. So that I will leave this here, right? And I will leave, this is where I'm going to insert my poll for the how big fact tables are out in the wild. I'll add that onto the end here. So that is it. That's all I had for this video. Hope you enjoyed it, and I'll see you next time.